Now we're ready to start Chapter 12, and in Chapter 12 you can see we're going to be dealing with proportions as opposed to Chapter 10 and Chapter 11 dealt with a characteristic on our data where there was a numerical value associated. Now our context is we have a certain population and we're going to measure a characteristic on this as far as whether the people have the characteristic or don't have the characteristic. Maybe it's being left-handed. And so let's say I had started with capital N being the total number of people in the United States, and I could count and find out how many of those people are left-handed, and that would give me a proportion or a little p, and that is a parameter. So there is a true proportion for the number of people who are left-handed in the United States, or the proportion of people who are left-handed in the United States. And remember what happens when we have a proportion. There is no standard deviation associated with this. There are a total number of successes out of a total number of people. And when we take samples of a specific sample size, we will get p-hats, and these p-hats will not all be the same. If we find the mean of all these p-hats, each coming from a sample size of n, these p-hats will center at p. So the mean of these p-hats will be at p. All these p-hats will be different numbers. They will not all be the same value. Some of them might be the same, but they definitely will not all be the same number, and there's a certain standard deviation that's associated with that. So these should look familiar from our study of a couple of the chapters in the past. Now, let's look at some characteristics. When we're sampling and collecting n values from a population, we do want our data to come from a simple random sample. We don't want bias. Likewise, remember we want our population to be greater than or equal to 10 times our sample size. And remember the reason for that is this standard deviation formula that we referred to already. That standard deviation formula is the formula when our sample is no more than 10% of our population. So it's not bad to have a sample that's larger. However, we would just use a different standard deviation formula if that were the case. There's a little multiplier that's another factor we have to multiply this standard deviation by, and we're not held responsible for that in this course, so we won't even cover that. Now, if we're going to perform a hypothesis test, we also want to double check and make sure that our sample size is large enough for us to be able to approximate our distribution to a normal distribution. And remember what we did to test for that. Now we would have for a hypothesis test, we would have a certain p-value proportion that we would be assuming that our population of interest is equal to. Say again, maybe if it were referring to these left-handed people, maybe I might assume that this proportion is 11%. So I might put a 0.11 here or 11% here. Now we need to sample large enough so that our expected values are at least 10. We would need to have our sample size times what we're assuming the proportion to be. We need the expected number of successes. That's what this would be. This would be the expected number of successes. That's this value. And we need the expected number of failures. That's what this value would be. The expected number of failures to both be at least 10. And remember from our previous experience with looking at sampling distribution, we need this to occur so that we'll have this approximate normal distribution. If these aren't at least 10, then we won't be able to use our normal approximation for this distribution. We'll come back to this for confidence intervals in a minute. So we're testing basically three things when we're going to do a hypothesis test about proportions. Simple random sample, so we don't have the bias. We want the population to be greater than or equal to 10 times the sample size so we can appropriately use this standard deviation formula. And we want to have the approximate normal distribution checking for at least 10 successes expected and 10 failures expected. We won't necessarily get in our sample 10 successes and 10 failures, but we want to expect that based on our null hypothesis. Again, we'll come back to that in a minute. So we have a test statistic for a hypothesis test. Remember, there'll be a certain p, a certain proportion that we're going to assume to be true, and we're going to collect data and get a p-hat I'll just plop the p hat here. It may not be in this position. It might be down here. It might be closer, and so on. And then depending on whether this is a one-tail or a two-tail test, we might be finding this for our p-value, or if it's a two-tail test, we might symmetrically be sketching this value on the opposite side and shading below. But notice what our test statistic will look like. We're going to take what we get from our p-hat, from our sample, minus what we're assuming the proportion to be, all divided by a standard error. And this standard error will be calculated using what we're assuming the proportion to be from our null hypothesis. Okay, so what we got minus what we're assuming all over a standard error. And that's how we consistently will find our test statistics for all the statistics we work with. Now let's go back up a second to the confidence interval. Sometimes I'll ask you, and the AP test will ask you, what type of assumptions do you have when you're going to be calculating a confidence interval for a p-value? And so, once again, we need simple random samples, and we need to have the population greater than or equal to 10 times the sample size. Now, for a confidence interval, we actually want the actual number of successes from our sample and the actual number of failures. These are actual values. We want the actual number of successes that you obtained from your sample and the actual number of failures you obtained from your sample to be at least 10. Because when we're calculating a confidence interval, we're not necessarily assuming that there's any type of null alternative hypothesis. We're just trying to find an interval estimate for our p-value. And look how we calculate a confidence interval. What you got, plus or minus, and we will use a z-star value here. We'll always use z's, not t's, when we're dealing with proportions, times the standard error. And our standard error will use the p-hat values that we get from our sample. It won't use any pre-assumed value as we did for our hypothesis test statistic. So let's look at a couple examples, and then we'll go on our merry way. Okay, so we're on number 8 right now, and I have, in a recent year, 73% of first-year students responding to a national survey identified being very well off financially as an important personal goal. And so a state university finds that from their sample, 132 of the simple random sample of 200 in its first year say that this goal is important. And so we want to check to see that we can safely use the methods for this value, for this section, to calculate a confidence interval or to perform a hypothesis test. So let's look at this. So we know that in order to calculate a confidence interval or a hypothesis test, we need a simple random sample. Secondly, we need our population to be greater than or equal to 10 times the sample size. So as long as at this college, if we're dealing with first-year students, as long as we have at least 2,000 first-year students, we're good to go. And then to calculate a confidence interval, we need to check and see, did we get at least 10 successes and 10 failures? And we actually know from right here, we're told that there were 132 successes, and we would have then 68 failures. And both of those are at least 10. Therefore, we can proceed with calculating a confidence interval. And remember, this is going to check for an approximate normal distribution so that we can use a z-value. So now if we're going to calculate the confidence interval, look how easy it is to do. What we got, plus or minus the appropriate z-star value for 95%, which we know is 1.96, and then times this standard error, which is the p-hat, 1 minus p-hat, so that's the probability of success, probability of a failure, all over the sample size. And the context of this means 95% of the time when we calculate an interval using this type of formula, 95% of the calculated intervals will have the actual parameter or the proportion that we're looking for within that. So this may not have the actual p-value for the entire university in there. However, 95% of the time when we do this calculation, you will have the capital or the little p that we're looking for in there. Now we're going to do a hypothesis test using the values that we had on the other side. And so when we calculate a hypothesis test, our assumptions are the same for the first two. And remember, the third one, the only little change is there's going to be a certain assumption that we're going to have for what the p-value is. And we're going to assume, is there good evidence that first-year students at the university who think being well off differs from the national average of 73%? And important words to read. Do we have evidence that they differ from the national average? So we're not proving higher or lower. We just want to find out if they're different. So here would be our hypotheses. And we're not disclaiming the national value. We're just trying to find out whether we have evidence that this university is different from the national level. So we'll assume they are 0.73, plot that in the center of our picture, and alternately, they're not equivalent to 0.73. When we do our third little assumption test, this is a different test, remember, than the confidence interval. This is how many do you expect as a success and as a failure. And so we would anticipate having 200 times our assumption. We'd expect to get 146 successes and 54 failures. Now, as long as those are at least 10, then this normal distribution assumption holds true. So I have the statistic that was calculated from the data was at 132 out of 200 in the sample. That was here. And since I'm doing a two-tailed test, I'm shading symmetrically in both directions. When I find the area of these two little tails, I'll have my p-value. Make sure you're writing the symbolism out correctly. This is not an x-bar, this is a p-hat. So we're finding the area of this little tail first. We need to convert it to its test statistic, what I got, minus what I'm assuming, all over the standard error. And remember, this standard error for the test statistic uses what we're assuming, 0.73, 1 minus 0.73 over 200. So there's what we're assuming that the standard deviation is of the sampling distribution of p-hats is. I get my test statistic, and I get my corresponding p-value. I used the normal CDF in order to calculate this. I could also look that up in the table. Now, I didn't give a significance level in the question, so I answered it under a couple of conditions. At a 1% significance level, we don't have evidence against the null. We would say that there does not appear to be anything significantly different between 73% for this university. So we don't have evidence because if we think of our p-value as compared to this significance level, it's above the significance level, so we would say that's just normal variability for a distribution centered at 73%. On the other hand, if we were using a confidence level or a significance level of 5%, we would say, well, 5%, this value is lower than my 5% significance level, so that would be considered unusual for a distribution centered at 73%. So we would say that we have evidence that it is significantly different, or we would reject our null hypothesis and conclude that the school does not have a 73% for this particular question that they were looking at. Now, let's turn over and we'll talk back about this little formula idea here just by looking at the example on the next page. So we have a national opinion poll found that 44% of all American adults agree that parents should be given vouchers good for education at any public or private school of their choice. The result was based on a small sample size. And we want to find how large of a simple random sample is required to obtain a margin of error of 0.03, which means plus or minus 3 percentage point in a 95% confidence interval. So if I look at an interval here, and I'll just use this marker here right now, we know that we get some type of a p-hat, and then it's plus or minus some z-star value times the square root of p-hat, 1 minus p-hat over n. And we know that this part is our margin of error. And so we're saying that we want to sample and have this plus or minus be no bigger than 0.03. So whatever you get here, and we apparently in one very small sample they got 44% to be here, that we want to know how large of a sample size right here, and we know that this n is going to control our sample size, we want to know how large should n be so that this margin of error is plus or minus 0.03. Now, let's say, again, we haven't taken a sample that is a large sample yet. It's just been a small one. So we're guessing it's probably around 44%, but it could be higher or lower than that. So if I use the 0.44 and I am using a 95% confidence interval, so there's the corresponding z-value. And if I think that this 0.44 is probably ballpark figure pretty good as far as being correct, and place that value here, 1 minus it there, and there's my unknown n, and I want that whole margin of error to be equal to 0.03. When I do the algebra, you can see I kind of split up this fraction so that I'd have a square root on the top and then a square root on the bottom. And multiply both sides by the square root of n and divided both sides by 0.03, and then I have to square both sides. And that ends up giving me, rounding up, 1,052 is how many people I would have to sample in order to get this margin of error to be this small for this setting. So that's quite a few people. Now, if you haven't taken a sample before, how would you know what to put in this value? Because they said in ours that they estimated it to be 0.44, so that's what they used in here in order to do the calculation. A conservative estimate, and that's what is referred to on the previous side of the paper that I just kind of skipped right now, is to say if you don't know what this value is going to be, a conservative estimate is just to guesstimate and say, I think it's going to be 0.5. And then 0.5 in these spots. And other than that, everything is the same as the previous one. And I go through and do the algebra, would give me a sample size of 1,068. So if I had no idea about what the percent would be for the p-hat that's going to come up from the sample, my best thing to do is to pick 0.5. That will maximize the sample size that I might need in order to have this confidence interval have a margin of error that is 0.03. Now, you won't necessarily always use 0.5 there. For instance, let's say you had a setup where you were looking at a population, say, in DeWitt, and you were looking at a characteristic of people who have, let's say you want to know what proportion of people are AB negative blood type. And you're going to take a sample and get a confidence interval that's going to look something like this. And you're deciding, well, how many people should I use in order to make this margin of error be, say, plus or minus 4%, so 0.04. Now, in this case, AB negative is a very rare blood type. Even in DeWitt, doesn't matter where you go, that's a rare blood type. So if you assume that this value here is 50%, 0.5, 0.5, figure out what size n with, say you're going to do 95% confidence, you're going to use a z-value here of 1.96. If you use 0.5 for your guesstimate of this p-value, you actually are going to sample way larger than what is really necessary, because this proportion of people is probably very small. Say in the adult population, maybe this only occurs with maybe, and I think I'm even exaggerating, 2% of the population. If I use a guesstimate of 2% here, 0.02, 0.98, and go through and solve for n and find out what sample size causes this margin of error to be 0.04, with 2% here as opposed to 50% here, putting in 0.5 here, the sample sizes will be tremendously different. So in general, if you have no idea what to put in this value, use 0.5. If you have an inkling that this is going to be something close to a small number, then use a kind of a large estimate for that small number, and that will tell you a better suggested sample size than what would be if you use 0.5. You can look in the book and read a couple examples on that too if you want more clarification. But that's it for right now. You're ready to practice.